Okay, students, now I am going to teach a problem on free convection, especially the external flow. In external flow case, there is a flow over the surface, particularly for horizontal plates and water. Here there is called as a plate. So the plate is immersed in water. So how much heat is that is transferred from horizontal plate to water by the means of uh, free convection. Okay, now we move to the problem. Here, the problem is the thin 80 centimeter long and 8 centimeter wide. Here, the plate is 80 centimeter long and 8 centimeter wide. Horizontal plate is maintained at temperature of that is 130 degrees Celsius. Here, you have the plate temperature that is a T wall, that is plate temperature that is maintained at 130 degrees Celsius in a which is kept in large tank full of water that is at 70 degrees Celsius. So T ambient that is equal to 70 degrees Celsius. Estimate the rate of heat input to the plate necessary to maintain the temperature of 130 degrees Celsius. So you are going to maintain the plate temperature as 130. How much heat is you are given to maintain the temperature is 130. Listen, in that case, the heat that is lost by the plate to water equal to that is heat given to the plate to maintain 130 degrees Celsius. So in order to maintain 130 degrees Celsius to the plate, so what is the amount of heat that is given to the plate which is equal to the that is what is the amount of heat that is given into the plate that is equal to the heat lost by the plate to the that is water. So first we find that there is a heat lost by the convection which is equal to that is a heat given. So first we find the heat loss to the convection. So before you proceeding the problem, you must know the problem is first case that is called as a free convection. You already know because the velocity is not given. Then second case it is external flow because no fluid is flow inside the plate or inside the cylinder. Third one you are going to find the whether the flow is laminar or turbulent. So for finding a laminar or turbulent, you need to find the some basic properties. What are the properties? First, you find that is called as a film temperature. That is, film temperature is equal to wall temperature plus ambient temperature divided by 2. Here, the plate wall temperature is equal to 130 degrees Celsius, and then film temperature is 70 degrees Celsius by what? 2. So almost by average, we are getting the film temperature is 100 degrees Celsius. Okay. So we have to evaluate the properties at 100 degrees Celsius. Properties at 100 degrees Celsius. Now we move to the property. Here the data book for the free convection. We clearly know what is the condition. Here it is that is a film temperature. Film temperature is equal to wall temperature plus ambient temperature by 2. Here now we can find the properties. So for the properties we can move to the page number. So this is a property. So please note that this is the same mistake done by you during the examination because if if you're going to find the property, defaultly we go to find the properties of air. But this problem, the fluid is water. So please be careful. You can choose the property for which fluid is given. So most of the problems are deals with the dry air. So frequently used to use the dry air data. So automatically we doesn't know we move to the whether the fluid is a water or liquid. We frequently use the dry air. So we can done a mistake there. So please careful. We can go to the property of water. Note that at water the 100 degrees Celsius. Please note that at 100 degrees Celsius we have the property. So we need only the kinematic viscosity, then Prandtl number, then thermal conductivity. These three properties are important. So one is the kinematic viscosity, next one is the Prandtl number, third one is the thermal conductivity. Then after that, we have another one more value that is called as the beta. Okay, so for beta, refer the page number 29. So for taking a beta values, we can move to the page number 29. So this is page number 29. For 100 degrees Celsius, for 100 degrees Celsius, this is the air. We do not require air. We need a water. So 100 degrees Celsius, the beta value is equal to 0.76 into 10 to the power 8. So carefully note the beta value and the property value, and we write it in the equation. Here, properties at 100 degrees Celsius, we know already noted. So we have that is a kinematic viscosity, that is mu is equal to 0.293 into 10 to the power of minus 6. Then meter square per second. Next one is the Prandtl number. Prandtl number is equal to 1.740. The next one is the thermal conductivity. We are having a 0.6687 watt per meter Kelvin. The next we have the thermal coefficient of thermal expansion beta. So beta is equal to 76 into 10 to the power of minus 3. So listen, so in previous cases for solving the problems in the air as a fluid, we simply taken that is beta is equal to 1 by Tf in Kelvin. So most of them use this equation beta 1 by Tf in Kelvin, but if you substitute the Tf in this equation, we are getting a wrong answer for this beta. So for case of water, better you take a property at HMT data book in the page number 26. So this is a totally wrong in a case of water. Okay. So after you finding the properties, you are going to find whether the flow is a laminar or turbulent. For this, we are needing the Grashof number. So what is Grashof number? So in the Grashof number, it is equal to G beta then L cube into delta T divided by mu square. So in some cases that can be written as G beta. In many cases it can be written as sorry. In some cases it can be written as G beta then x cube into delta T divided by that is a nu square. So instead of using x we are using that is called as L. So in a case of horizontal plate we have some formula to find a L. So L is nothing but that is called as a characteristic length, that is in a case of horizontal plate. So that is can be calculated from the formula, that is surface area divided by perimeter. Sorry, surface area divided by perimeter. So here the surface area divided by perimeter. Here what is the surface area? Surface area of plate is nothing but that is a length into width divided by perimeter is equal to 2 into length side. 2 into length plus width. So we are calculating that is 80 into 8 divided by 2 into that is 80 plus 8. So after substituting this value, we are getting then L is approximately that is equal to 3.63. So for this convenient, so the standard value that is given in the book, that is approximately L is equal to approximately that is W by 2. Here the W is equal to 8 centimeter, 8 centimeter by 2, that is equal to 4. So here that they have a two approach you are going to find the L. One is by formula we finding that is equal to 3.63, or by for a standard value, the standard notation that given in the data book, for that you are going to find that is equal to 4. So for better, we have L is approximately that is a W by 2. This is a standard formula provided for all the cases of horizontal plate. So for by using this formula, we have a value that is equal to 4. So substitute the 4 in the that same formula. Okay. Now we move to the next one. Here there is a G R is equal to G beta then L cube into delta T divided by that is a nu square. Here G, that is called as a gravity, already you know 9.81. So beta from the property table you have these terms 0.293, sorry 0.76 into 10 to the power of minus 3 into L, that is a 0.04. Better you substitute in meter, not in a centimeter. Here 4 is a centimeter, in a meter you have consider 0.04 meter cube into delta T. Delta T, that represent, that is equal to wall temperature minus ambient temperature. Here wall temperature minus ambient temperature. Wall temperature is 130. Here minus, that is 70. You are getting 60 divided by, that is nu square. Nu square is equal to 0.293 into 10 to the power of minus 6 whole square. So after substituting the above values in the equation, we are getting the guess of number is equal to 3.33 into 10 to the power of 8. That is called as a guess of number. But in a case of finding the flow is laminar or turbulent, we are needing a value of, that is a GR, PR, GR. So here GR is 3.348 multiplied with the help of PR. PR is equal to, that is 1.740. Previously you find from the property table PR is equal to 1.730. So after substituting the value, we are getting a ZR PR is equal to almost 5.802 into 10 to the power of 8. So this is the value you got. Then we move to the data book to find the exact Nusselt number. The next condition is, that is called as a Nusselt number. We are going to find heat transfer coefficient. So in that case, we having a two Nusselt numbers. So what does that mean? In the horizontal type of plate, one surface having upper surface, the another one is called as a lower surface. We are considering two cases, that is upper surface and lower surface. What happened in the both the surfaces? So for that category of horizontal plate, in the data book, right? Listen, in the data book, so for case of in a free convection page, in the free convection page, so it is less to 10 to the power of 10 to the power of 8, sorry 10 to the power of 9. It is in nearer to the turbulent cases. So here for horizontal plate, this condition is whether it is a laminar or a turbulent. This particular case is for the horizontal plate, whether the upper surface is heated or lower surface is cooled. So in our cases, we are having a GR PR is equal to 5.8 into 5.8 into 5.8 into 10 to the power of 8. This is the GRPR value we are getting. So it is horizontal plate, is one is upper surface heated or lower surface cooled at constant wall temperature, because if we indicate the temperature is 130 degrees Celsius. So this condition exactly suitable. Here it is between the value of 10 to the power of 8. So this is the condition exactly chooses, because it is between the 10 to the power of 8, 10 to the power of 6 to 10 to the power of 11. So this condition is suited. So we can choose this Nusselt number. Here the upper surface is heated, because you have to maintain the condition to maintain the temperature of, say, that is called as a 130 degrees Celsius. Okay, so we can choose this condition. And then similarly for a bottom surfaces, So lower surface, it is also that is heated to maintain the temperature, say 130 degrees Celsius. So for that we have this value, that is GRPR is equal, already we know that GRPR is equal to 5.8 into 10 to the power of 8. This exactly lies in this category. So for that we are choosing this Nusselt number for, that is called as a bottom surfaces. So top surface we are having a one Nusselt number, in bottom surface we are having another one Nusselt number. Okay, now we write the Nusselt number in the PowerPoint presentation. Here, first Nusselt number for a top surfaces. For a top surfaces, we have a Nusselt number. Then Nu is equal to 0.15 into GRPR whole power 0.333. So this is exactly suitable. So we know that is Nusselt number is equal to 0.15. GRPR, you know, that is a 5.802 into 10 to the power of 8 whole power 333. We are getting the Nusselt number at the top surfaces. It is a top surface. Now top surface that may be equal to, that is 124.27. From the top surface Nusselt number, you are going to find the heat transfer coefficient. So which is equal to, that is HT, that is L divided by K. So already you know that is L, that is L is equal to 4. Thermal conductivity you may taken from the properties is equal to 0.6687. You know unknown value, that is equal to HT. So HT is equal to, there is Nusselt number at the top surface into thermal conductivity divided by, that is called as the L. So there is a 124.27 into 0.668, thermal conductivity is 0.6687, divided by, that is L, that is equal to 0.04. Then you are finding the top surface, that is a Nusselt top surface heat surface coefficient, that may be approximately, which is equal to 2,117 watt per meter square Kelvin. So you find one heat transfer coefficient, that is on the top surface. Next one is you are going to find the, that is called as the bottom surface. So bottom surface, we already note the formula in the HMT data book. Then Nu bottom, that is equal to 0.27 into GRPR whole power 0.4, or 1 by 4. Okay, then already know GRPR, which is equal to 5.8 into 10 to the power of 8. 1 by 4 we can be written as 0.25. So Nu bottom, that may be all, which is equal to approximately 41.8 value as a number. So which is equal to the H of bottom into L divided by K. L divided by K. You know all the values except HB. You are going to find that is a HB is equal to Nusselt number at the bottom surface into thermal conductivity divided by L. So Nusselt number, you know, 41.8 into thermal conductivity point 6687 divided by L, that is 0.04. Then after substituting these values, you may have the H of the bottom surface is equal to approximately equal to, that is 710 watt per meter square Kelvin. You find the two heat transfer coefficients. So one is at the H top surface, then next one is the bottom surface. So then you find the heat transfer, that is heat transfer that maybe takes place on the both the sides. So Q is equal to Q at the top plus, that is the Q at the bottom. Here you have, that is the top surface, the HT into, that is area into delta T, plus for a bottom surface here HB area into delta T. So for in the both the equations, area and delta T is a common. So it can be again rewritten as HT plus H bottom into area into, you're getting some error there, HT plus HB into then area into delta T. So better you can Go to the next slide. So here, so Q is equal to HB plus, sorry, H top plus H bottom into area into, that is called as a delta T. So here is equal to HT plus HB area, you know, that is a length into width into delta T, that is equal to TW minus T infinity. So HT you can find from the value, that is 2117, HB is equal to 720. So 2117 plus 710, sorry, 710 into length is equal to 0.8 and wide is equal to 0.08 into wall temperature is equal to 130 degrees Celsius minus ambient air water temperature is equal to 70 degrees Celsius. So after substituting the approximate absolute values, you may find the heat transfer that may be equal to the, that is 10,850 watt. So approximately that is equal to 10.85 watt. So this much Q is equal to 10.85 watt. So the heat given into the plate to maintain the temperature of 130 degrees Celsius, which is equal to, the heat given into the plate is equal to 10.85 kilowatt. Sorry, here it can be written as, that is a kilowatt. Kilowatt is necessary to maintain the temperature of 130 degrees Celsius if the same plate is, that is kept in a water at a 70 degrees Celsius. So some amount of heat is lost to this, lost to the water. So the 10.85 kilowatt heat is necessary to maintain the plate temperature 130 when it is kept in a 70 degree Celsius water temperature. Okay, thank you. So please be careful. You have two mistakes. You have done the two mistakes in the problem. One is the, there is a property selection. Property selection. So that may be air, not air. That is a water. You please be careful. You select the properties at a water. Second condition, beta. So in a beta, everybody know, right, that beta is equal to 1 by TF in Kelvin. That is not appropriate for this case of water. So for water, you can take it from the data book. So beta for water can be taken it from the data book. Then third one is the plate is horizontal kept in a water. So you have to find two Nusselt number and two heat transfer coefficient. So H at the bottom, H at the top, two heat transfer coefficient you are going to find. So these three are the important consideration in this problem while you are solving in the examination. Okay, thank you.